Ladies and gentlemen, hello and welcome. Coming to you not quite live from One Take Studios, because one take is all we need because we don't have time to do retakes. Today's topic for statistics is simple random samples as the primary target for random samples in general. So much of statistics requires that good data has been collected, and a simple random sample allows us to do that. It can be used in several formats, so we're going to start with this one because this is kind of like the groundwork for everything else. By definition, a simple random sample, n measurements from a population, is a subset of the population. Pause. N is a variable. So we're saying that we've got n number of data pieces, measurements, is a subset of the population. So for the fun of it, if I have a population of 100 numbers, n might be a subset of 20, 20 out of the 100. Or maybe n is 12 out of the 100, or 72 out of the 100. So this is a variable and it can change. This n is selected in such a manner that every sample size n from the population has an equal chance of being selected. The words that our brain usually latches onto is this idea of having an equal chance of being selected. And while as individuals we would like to have an equal chance of being selected for things, we have to go beyond that. Notice it says every sample size n. So if n is 1, that means that every one person, because one person could be a subset, or every one thing has a chance of being selected. So if we have a sample where we have certain elements that have no chance of being chosen, that's problematic. That would not be a simple random sample. But we have to grow that idea as well, because what if n grows? What if n is larger? So let's say that my sample size is 5. That means not only then does every individual one element have to have a chance of being chosen, but every single group of 5 within that population has to have an equal chance of being selected. To understand that, it's almost easier, I think, if we look at a population with an arrangement that is not a simple random sample. So let's say I've got groups 1, 2, 3, 4 individuals there, and 1, 2, 3, 4 individuals there. 1, 2, 3, 4. 1, 2, 3, 4. I've got a group of 16. What would we consider a simple random sample? Well, every single one of these individuals has to have a chance. So that guy right there has to have a chance of being selected. That guy right there has to have a chance of being selected. But so does every single subgroup, every subsize. So let's say that out of this population of 16 that I wanted to select 4. Well, I know, maybe I'll just choose one of these groups. Because if I choose this group, each of these guys would have a chance of being chosen. Or if I choose this group, each of these guys has a chance, everybody's got a chance, everybody's got a chance. Here's the downfall. Every group of size 4 has to have a chance. That means what if I want this person and this person together with this person and that person? If I'm just picking one of my groups of 4, yes, individually, every individual would have a chance of being chosen as one of those groups of 4, but that group of 1, 2, 3, 4 has no chance of being selected. And so every sample size has to have a chance of being selected. So how do we make that happen? Well, that means that I can't choose just one of the groups and calling it good. All right, so that's not going to work. What if I choose one person from each group? I could choose one from this group, and then one from this group, and one from this group, and one from that group. That would work, right? And again, that does mean that every individual does have a chance of being selected. However, again, 2 people from the same group is not a possibility. And I need every group of 4 to have a chance. So what does that leave? How do I get every group of 4 to have a chance? So that if this one and this one and this one and that one were together, that would be a group of 4 that has a chance of being selected. This is ultimately what makes it a simple random sample. Even though the word simple is there, it's a little bit more complicated sounding. I need something truly random that involves all individual pieces, not just groups or chunks. So maybe I take all 16 of these guys and I throw them in a hat and I start pulling things out of a hat. What if I pulled 4 of these out of a hat? Would every single individual have a chance of being chosen? Yes. Would every single group of 4 have a chance of being chosen? Yes, that's actually possible. So pulling names out of a hat, pulling whoever, bottle caps, whatever it happens to be, whatever your individuals are, pulling things out of a hat is actually a really good simple random sample. Maybe you're a little bit more technologically minded than that, and you would rather not cut up pieces of paper and put them in hats. What about a random number generator? What if I numbered these guys? There's number 1, 2, 3, 4, 5, 6, 7, 8. If I give them all a number, and I get my random number generator, which most calculators will have them, and you can find them online as well, and I say, random number generator, please pick numbers between 1 and 16. You simply take the first 4 that the program gives you. That would also be a simple random sample, because every individual has a chance of being chosen, and every group of 4 also would have a chance of being chosen. All right, so simple random sample, that's kind of a big deal. We're going to be going back to that one several times, I think. But SRS, because that's a mouthful, SRS becomes the abbreviation that I'm going to use to refer to a simple random sample. I'm going to jump away from this for a moment and kind of pull up other techniques that we might use. So other sampling techniques, this is also considered to be largely random, although one of these is definitely flawed compared to the others. If we are looking at other techniques, stratified samples are a possibility. Idea of a stratified sample is that my population has groups within it, and those groups are defined by having something in common. So I like to think about in a high school setting, freshman, sophomore, junior, senior. The population would be the entire student body. But each class is a strata. All freshmen have being a freshman in common. All sophomores have being a sophomore in common. The idea with stratified then is I'm still going to take a simple random sample, but I'm going to choose some from each of the strata. So that if I would like to have a group of 100 as a sample coming out of my population, of my student body, instead of just randomly taking any 100, I take 25 from the freshman class, and 25 from the sophomore, 25 junior, 25 senior. That way every class is represented as part of my sample. Within that, there is still the simple random sample, because I would do a simple random sample to select 25 out of the freshmen, and then 25 sophomores, juniors, seniors, etc. So you are still doing a simple random sample, but it's after you've identified these groups and saying that I'd like to have each of these groups represented in my data that I'm collecting. Systematic is another way to do this. Systematic would be along the lines of, we talk about population arranged in a natural sequential order. What would that look like? That could be alphabetical. Maybe I've got a whole bunch of people and I have a list of their names alphabetically. Maybe I've got a bunch of things and I assign each one a number and I put them in line numerically. Think about if you were just to line a whole bunch of people up against a wall in the gymnasium. If they're in alphabetical order, Systematic would say, I'm going to take, random starting point, the 10th person. And I'm going to take every third person after that. So I'm going to take the 10th person, and the 13th person, and the 16th person, and the 19th person. That is how systematic works. Is systematic a simple random sample? No. Individuals still all have an equal chance of being selected. However, because you are taking every, nth? Yes, every nth element, because you're taking every fourth or every fifth or every sixth in your lineup, elements that are right next to each other have no chance of being chosen together. So is systematic a good way to pull together a sample? Yes. Is it simple random sample? No, it is not. Cluster. Cluster and stratified, these two kind of get confused with each other on occasion. Often refers to taking a demographic area and dividing it into sections. Maybe think of something along the lines of zip code or area code. We could even do states. So the U.S., let's say that the entire U.S. population is our population and that the sections are states. This says that we're going to randomly select sections. This piece of it is still a simple random sample because we're saying out of all 50 states, we're going to select a handful of states. Let's say that we're picking 5 out of the 50 to represent the country. The difference is this. Stratified would say that out of each state, I'm going to choose a representation and I'm going to have some people from every state. Cluster does not work that way. Cluster says I'm going to choose 5 states, and I'm going to choose every single person in that state to be represented as part of the sample. So if Michigan gets chosen, every person in Michigan is part of the sample, not just some of them. If Hawaii gets chosen, I would choose Hawaii. That way I could go to Hawaii. That'd be fun. Every single person from Hawaii would be in the sample. So notice the difference. Here we've got groupings. We're taking some from each group. Here we've got groupings. We're taking all from some of the groups. So some people from each group, all people from some of the groups. Big difference there. Convenience is convenient, and that's temporally, that's not the word I'm looking for, potentially problematic, because we are talking about the results or data here are things that we can easily get. So I'm collecting data, but I don't feel like getting out of my chair. I might just ask the first 5 people that walk by me what they think about a topic, and yeah, there we go, there's my sample right there. This runs the risk of extreme bias. This is not considered good math, good science, good sampling techniques, but it is a thing that people use on occasion, hence it has a name, all right? So definitely not a simple random sample right here. But these two have elements of simple random sample. This one is not simple random sample, but is still good sampling techniques. All right, what else do we have going on here? We also have, oh, I know what I'm going to do. I'm going to turn this over. We have, eeny, meeny, miny, mo, a couple of other things that I want to talk about. One of them is the idea of, where'd it go? A sampling frame. All right, a sampling frame. And so with the sampling frame, we want to think about how the frame represents the population. So let's say that this hard-sided box, think about it like a weird Venn diagram basically, represents every single person in the population. Why is my camera out of focus? There we go, that's better. All right, so it represents every single person in the population is inside this rectangle. When I go to choose my sample, how many of these people should be eligible for sampling, to be chosen? Well, hopefully all of them. So my lovely dotted line here, we are saying that the size of my sampling frame needs to mimic the size of my population. Because really what I want is I want everybody in there to have the potential to be chosen. And if that's true, that means I have a good sampling frame. Good sampling frame. Smiley face. There we go. But what if again, the rectangle represents my population, but when I go to choose my sample, only these people within this boundary have the chance of being selected. If my sample comes out of this group, and all of these people in the population don't even have a chance of being sampled, that's not going to be a very good representation. This is what is called undercoverage. There we go. Undercoverage. And you might have guessed, this is not ideal. This is unhappy. So you want your sampling frame to match your population, because if your sampling frame is too small, you're not going to get a good representation within your sample of your population. Other things, odds and ends here I'd like to add in. I want to talk about sampling error. Particularly sampling error versus a non-sampling error. Sampling error versus a non-sampling error. All right. These get kind of twisted around by a lot of people. A sampling error is not actually a bad thing. We hear the word error and we're like, well, errors are bad, aren't they? If we're talking about using a sample to represent a population, the sample itself is not the entire population. So therefore, the data that I collect here may not match the data for my population completely. Let's say that I have, I don't know, again, let's go back to having a student body, and somehow we've done a simple random sample, yet selected a whole bunch of guys on the boys basketball team. and we're collecting information about shoe size. If I've chosen a bunch of guys on the basketball team, what is the likelihood that their shoe size is going to reflect properly the shoe size of the entire population, including all of the teeny tiny freshman girls? Maybe not so much. Does that make it a bad thing? No. By agreeing to allow a sample to represent a population, these errors may simply occur. So this is just a difference, I'm abbreviating here, difference in measurements between, hole in my paper, between, I don't like that, the sample and the population. We are simply saying that because we have chosen to use a sample to represent the population, the measurements between the two might not match up perfectly. That's okay. That happens. A non-sampling error is also an error, but this is not an error that comes as a result of sampling, hence non-sampling. This is an error that comes as a result of something else. This can be the result of delightful things like poor design. Maybe you didn't really think this through very well and you've just selected something that's not really a good sample overall. Maybe you tried to do convenience. Maybe you just chose sloppy data collection. Yeah, something like that. So we're talking, these are things that would have been preventable. These errors are not as a result of sampling, they're a result of something else that we could have done better. So sampling errors, while not ideal, happen, and we're okay with that. Non-sampling errors are problematic, and these are the ones that we want to try to avoid more than anything else. All right. I think that we are going to stop there today. I guess I do want to mention one more thing. Sometimes we run simulations on things because on occasion, it's not a good idea to get samples from real life, saying things along the lines of, nuclear reactions. I don't want to just try a couple of things in nuclear reactions as a sample to see what happens and accidentally, destroy the planet. So maybe I run a simulation instead. I get computers to figure out what might have happened or would have happened as a result of data coming together. So sometimes sampling is not really a great option overall, but doing a simulation might be a good option instead. All right. Thank you very much. Talk to you soon.